In this lecture, we will start our discussion of curvilinear coordinates. So far, we have discussed a Cartesian coordinate system, where, for example, the surfaces of constant z, the coordinate z is along the direction of variation of the concentration, temperature or velocity field. So, direction of variation is the z direction, and the surfaces of constant z are planes. The surfaces of constant z are planes, and therefore, when we constructed our differential volume, we took a cubic volume in which the surfaces of the volume are all planes, in which the surfaces of the volume are all planes. So, because of that, the surface areas of opposite sides of this differential volume are equal in all cases. There are often situations where the boundaries may not be flat. In all of the problems we have solved so far, the boundaries have been flat, and therefore, the boundary was a surface of constant coordinate. The boundary was a surface of constant coordinate. There may be cases when the boundary is not a surface of constant coordinate. For example, for the flow in a pipe, the pipe is a cylinder, and on this wall of the pipe, the distance from the axis is a constant. So, if this were the z direction, and you have two orthogonal directions x and y, x is upward and y is out of the plane, and the pipe had some radius r, the pipe radius was r. The equation of the surface, the equation of the surface of the pipe is that of a circle in the xy plane, square root of x square plus y square is equal to r, or x square plus y square is equal to r square. So, that is the equation of a surface. Recall that when we had done unidirectional transport in Cartesian coordinates, we had imposed boundary condition at a constant value of z. We had imposed boundary conditions at a constant value of z. If we want to do a Cartesian coordinate, if we want to analyze this problem of transport in a cylinder or a pipe in a Cartesian coordinate system, the equation for the boundary is complicated. X square plus y square is equal to r square. The boundary is not a surface of constant coordinate, and therefore, it is difficult to apply boundary conditions at this boundary, which is not a surface of constant coordinate. So, what is the solution? One solution is, of course, to use the same equations that we had derived earlier, but in this case there are two coordinates x and y. So, if there is variation in the mass or energy only across the cross section of the cylinder, there are two directions here, x and y. So, you cannot treat it as a unidirectional problem. Even if you solve the equation in 2 dimensions, the equation for the boundary is complicated. So, it will be difficult to apply boundary conditions here. Similar thing applies for a sphere. If you have a sphere with center at the origin in a 3-dimensional coordinate system, the boundary is at x square plus y square plus z square is equal to r square, if r is the radius. So, you have to apply the boundary condition at a surface whose description in the Cartesian coordinate system is complicated. So, that is one option. The other option is to use a coordinate system in which the surface, the boundary, is a surface of constant coordinate. Those are called curvilinear coordinate systems, because the boundary, the surface of constant coordinate is a curved surface. It is no longer a planar surface, but rather the surface of constant coordinate is a curved surface. So, how do we define the surface? Okay. So, let us say I have a cylinder with an axis. Okay. Then I have to choose a coordinate system such that one of the surfaces is a surface of constant coordinate. That coordinate has to be the distance from the axis, because the surface of the cylinder is at constant distance. So, one of the coordinates that I choose has to be the distance from the axis. The second is the distance along the axis. Okay. So, if I look from above, right, one of the coordinates is the distance from the axis, and the other is the distance along the axis in the plane perpendicular to the axis. Okay. There is a third coordinate, of course, which is the angle made by with respect to any particular axis. Okay. So, in general, my distance from the axis will be one coordinate. The next will be some angle phi that is made with respect to one particular direction, usually what is called the x direction in this case. In the balance equations that we will derive here for unidirectional transport, we will assume that there is no variation in the phi direction, and the temperature depends only upon the radial direction, the temperature or the velocity. Okay. It does not depend upon the phi direction. Okay. So, that is the assumption. So, obviously, since the axis is not a distance from a plane, but rather a distance from an axis, since the coordinate is not the distance from the plane, but rather a distance from the axis, the differential equations that we get by a balance will also be different in this case. Okay. However, the procedure is exactly the same. We choose a differential volume between two surfaces which are surfaces of constant coordinate. Write a balance for the energy or the mass within that or even the momentum within that differential volume, divide by volume, divide by time, okay, and take the limit as delta t goes to 0 and the delta r goes to 0, and from that we will get the differential equation. Okay. So, let us do that, okay, for this particular case. This is the axis. Okay. I will choose a cylindrical differential volume. Okay. Cylindrical differential volume. Between two surfaces of radius r and r plus delta r. Okay. Two surfaces of constant coordinate. Okay. If I look at this from above, okay, the inner surface is at a distance r from the axis, and the outer surface is at a distance r plus delta r. Okay. And this height I will call it as delta x. Okay. This height I will call it as delta x. Okay. So, I have two surfaces in the r coordinate, okay, at r and r plus delta r, and two surfaces in the x coordinate at x and x plus delta x. Okay. And I will assume for the present that the variation is only in the r direction. Okay. So, this is the radial coordinate r, this is the axial coordinate x. Okay. And I am writing a balance for this particular differential volume. this annular differential volume between two cylindrical surfaces, first one at r and the second one at r plus delta r. Okay. So, that is where we are writing the differential balance. Okay. Okay. So, for this area of surface at r, okay, area of the surface at r is going to be equal to the perimeter times delta x, that is 2 pi r delta x. Okay. That is the area of the inner surface at r. Okay. The cylindrical surface area, okay, is equal to the perimeter of the circle 2 pi r times the height delta x. Okay. Area of surface at r plus delta r is equal to 2 pi into r plus delta r times delta x. Okay. Note that the areas of these two surfaces are different. Okay. The surface at r has a smaller area 2 pi r delta x, and at r plus delta r has a larger area 2 pi into r plus delta r times delta x, and the volume is equal to the perimeter 2 pi r into the thickness delta r into delta x. Okay. Delta x is the height, and this area that I just shaded for you has to be equal to 2 pi r, which is the perimeter, times delta r, which is the thickness. Okay. Okay, so we have to write a balance for this. Change in energy in differential volume. In time delta t. Rho Cp, okay, as we have been doing so far, I will assume that rho and Cp are constants, valid for incompressible fluids where rho is a constant, and I justified for you that Cp is a constant for most fluids over normal temperature ranges ranging from 0 to 100 degrees or so. Okay. So, rho and Cp are constant into the temperature at R T plus delta T minus the temperature at R T. Okay. That is change in energy in the differential volume. Okay. Energy in at the surface at R is QR at the surface at R. Okay, the energy that is coming in at the surface at R. Okay. Energy in is equal to, okay, the flux, which is energy per unit area per unit time at the location R, into the area. Area of the inner cylinder is 2 pi r delta x, okay, times delta t. Okay. My apologies, the change in energy in the differential volume, what I have shown here is the change in the energy density. I have to multiply it by the volume. Okay. I have to multiply this by the volume to get the change in energy. Okay. What I have done so far is only the change in energy density. So, I have to multiply this by 2 pi r delta x. Okay. I have to multiply this by 2 pi r delta x. So, this is the energy in at the surface at R. Okay. Energy out is equal to QR at R plus delta R. The surface area is now different, 2 pi into R plus delta R delta x into delta t. And the production of energy is going to be equal to the production per unit volume per unit time times 2 pi r delta x, that is the volume, times time delta t. Okay. So, therefore, substituting all of these together, I get rho Cp into T at r 2 pi r delta x, I am sorry. Surface area is 2 pi r delta x, 2 pi r plus delta r delta x, okay, plus SE into 2 pi r delta x delta t. Okay. Let me just write it all over again. So, this is the difference equation. I have to divide throughout, this is the balance equation for the energy. I have to divide throughout by volume and time to get a differential to get a difference equation. Okay. Divide throughout by volume and divide throughout by time. Okay. When I divide throughout by volume, I will get rho Cp into T at r T plus delta T minus T at r T divided by delta T. Okay. You have this factor of delta T on all the terms on the right side. You have to divide throughout by that factor as well as by volume. Okay. The factors of 2 pi will actually cancel out everywhere. Okay. So, I do not have to carry that factor around. Okay. And on the right side I will get QR at r times r minus QR at r plus delta r times r plus delta r, okay, divided by r delta r. Okay. Note that these two are different. Okay. The surface areas are different for the surfaces at r and r plus delta r. Okay, and it is important to keep that in mind when we do the simplification. Surface areas are different. Okay. The last term, of course, I divide by volume and time, I will just get SE. Okay. And this difference r times QR at r minus r plus delta r times QR at r plus delta r divided by delta r. Is the derivative of r times QR. Okay. Derivative of r times QR is r QR at r plus delta r minus r QR at r. Okay. This is the negative of that. So, I can write this as minus partial of r QR by partial r. Okay. So, that is how I will simplify that, and then you have another factor here of r. So, on the left side I have rho Cp partial t with respect to partial time, okay, is equal to minus 1 by r d by dr of r q r plus this source term. minus 1 by r d by dr of r q r. And then I can substitute Newton's law, Fourier's law of heat conduction. Q r is equal to minus k partial T by partial r. Okay. And I will get rho C p partial T by partial T is equal to 1 by r d by dr of r k partial q r by partial r plus S e. Okay. And I can divide throughout by rho C p. Okay. So, I will get partial T with respect to time is equal to 1 by rho C p r my apologies here, I substituted for this in terms of temperature, so I should get partial T. And if the specific heat and the density are constants, I can take this inside and I will get 1 by r d by dr of alpha r partial T by partial r plus S e by rho C p. Okay. So, this is the energy balance equation. Okay. Further, for constant diffusivity, I can take alpha outside. Partial T by partial T is equal to So, that is the form of the equation for constant diffusivity. Okay. Compare this with what we had for a Cartesian coordinate system. Okay. There, if you recall, partial T by partial T was equal to d by dz of alpha partial T by partial z plus S e by rho C p. Okay. And constant diffusivity, it was partial T by partial T is equal to alpha d square T by dz square plus S e. Okay. So, these were for constant diffusivities. Okay. Cartesian coordinate system, note that this differential operator on the right side multiplying the diffusion term, okay, or this differential operator multiplying the diffusion term is simpler than this particular differential operator. Okay. Similarly, in a Cartesian coordinate system, when expressed in terms of the flux, this was equal to rho C p partial T by partial T is equal to minus partial q z by partial z plus S e. Okay. So, this differential operator was a first order differential operator. Okay. This, on the other hand, is slightly more complex. Okay. This differential operator is more complex. So, that is the change in the balance equation for a curvilinear coordinate system. Okay. Because we had modified the bounding surface to be a surface of constant coordinate, the differential operator changes, okay, for the diffusion term. The reason is because surface area is changing. Okay. What we had written was a balance for the heat transfer rate. Okay. What we had written was a balance for the heat transfer rate. Now, in a situation where the heat transfer rate is the product of the flux and the surface area. Okay. The heat transfer rate is the product of the flux and the surface area. For this differential volume, the surface area is changing. Okay. So, even though the flux may be a constant, the heat transfer rate will change because the surface area is changing. or alternatively, if the heat transfer rate has to be the same at both the surfaces, that means that the flux times the area has to be the same at both surfaces. Okay. For a steady problem in the absence of any sources in sink, the heat transfer rate across both of these surfaces has to be the same. What that implies is that the flux times the surface area has to be the same, or the flux has to be inversely proportional to the surface area. Okay. And it is for that reason that you have this additional term of 1 over r d by dr of r times t, partial t by partial r here. Okay. So, that is the additional price that you pay, okay, when you have when you use a Cartesian curvilinear coordinate system in which the surface area is changing with distance from the axis. Okay. The surface area is changing with distance from the axis, and therefore, the heat transfer rate is the product of the flux and the surface area. And since the surface area is changing, that also has to be incorporated in the expression for the heat transfer rate. Okay. So, this is the energy balance. Okay. You can do mass balance in a very similar manner, okay. And what you will get, as I said, to go from energy to mass balance, convert temperature to concentration, thermal diffusivity to mass diffusivity, energy source to mass source. Okay. And you will get partial C by partial T is equal to 1 by R d by dr of thermal diffusion coefficient R partial C by partial R plus S. That is when expressed in terms of the concentration field. If you express it in terms of the flux, you will get partial C by partial T is equal to minus 1 by R d by dr of R times Jr plus S. And if the diffusion coefficient is independent of position, then this equation can be simplified, okay, and you will get partial C by partial T is equal to d by R partial by partial R, R partial C by partial R plus S. Okay. So, this is the energy balance. So, this is the mass balance equation. Substitute concentration over temperature, mass diffusion coefficient for thermal diffusion coefficient, and mass production rate instead of thermal production rate. Okay. Momentum balance is a little more complicated. Okay. That is because momentum is a vector, as I have said before. Therefore, one has to be careful while doing the momentum balance equation. Okay. I will start momentum balance in the next lecture. I will not go through the entire derivation, but I will just give you what the final results are, okay, for momentum balance. Okay. So, that the mass and energy balances are both equivalent, because you can substitute temperature for concentration, thermal diffusion coefficient for mass diffusion coefficient. Okay. The momentum balance is a little more complicated. I will discuss that in the next lecture before going on to discuss steady state transport. I will continue that in the next lecture. I will see you then.